Welcome back to my channel, and today I'm going to be talking about real analysis. In our previous video on real analysis, we're going to be talking about some of the most fundamental and important concepts in mathematics itself. We talked about number systems, number fields, and how to prove that the square root of 2 is irrational. In this video, we're going to be talking about other concepts, such as set builder notation, and we're going to be talking about the order axiom. Lastly, we're going to be talking about how to prove that the absolute value of A is less than or equal to B if and only if negative B is less than or equal to A, which is less than or equal to B. So let's begin by talking about set builder notation. So what is set builder notation itself? Set builder notation can be defined as a system that encodes the specific characteristics and logistics of a set itself. Now over here, we have an example of set builder notation in action. Now, as one can see, one can probably deduce that this probably represents the rational numbers. Now, probably because we have P over Q and Q does not equal 0. But it's important to realize that when dealing with set builder notation, we have to consider everything. For example, if this was not the integers, rather it was switched to something else. For example, let's just say it was switched to the natural numbers. Then this wouldn't be the rational numbers. If it was switched to the natural numbers, this would not be the rational numbers, because the rational numbers include negative numbers, but the natural numbers don't. So it's important to realize that we have to consider everything. But over here, this set builder notation example does represent the rational numbers. Okay, so let's talk about the fundamentals of set builder notation. This is the statement. The statement over here is the arithmetic manipulation of the variables involved. Some people just call it the variables, but over here we have division. So it's more proper and more specific to just call it the statement. We're stating what's happening with the variables. Now over here we have the conditions. The conditions are what are implied on the variables in the statement. This represents the two words such that. And such that, for instance, just represents that we're transitioning from the statement to the conditions. So this reads P over Q such that P and Q is are in the integers and Q does not equal 0. So that's what this whole statement or whole set builder notation represents. Now we can call this the whole statement, but if we just want to keep the minor characteristics important, this is the statement, this is the conditions, this is the such that. So this whole encryption of the set represents the rational numbers. So over here, I'm going to be writing an example of set builder notation. So let's say we have x squared plus 1 such that x is in the natural numbers and x is greater than or equal to 5. If we were to do this, then we can write an arbitrary amount of elements in this set. So we have to answer 3 questions. Number 1, write 5 elements of this set. Number 2, what is the characteristic of this set depending on whether it's infinite or finite? In other words, is this infinite or is this finite? And the third question, well, does it go in both directions or does it just go in one direction towards infinity? So let's first list 5 elements. Notice that this has to be the natural numbers, so no negative numbers involved, no zeros, no decimals, no fractions, etc. Now, x is greater than or equal to 5. So let's start off from 5. 5 squared plus 1 is 26. 6 squared plus 1 is 37. 7 squared plus 1 is 50. 8 squared plus 1 is just going to be 65. 9 squared plus 1 is 82. 1, 2, 3, 4, 5. Now that we've gotten this, is this set infinite or finite? Now, seeing that this is the natural numbers, which is infinite, and we can see that x is greater than or equal to 5, which means that it can be anything greater than or equal to 5, and anything greater than or equal to 5 is infinite in terms of extent. Therefore, this is an infinite set. Now, is it infinite in both directions or one direction? It's only infinite in one direction. Because if you think about it, you can't go below 26 because x can't be less than a 5. So it's important to realize this is infinite in only one direction. Now, the reason set builder notation is very prominent and very useful is primarily because of its usage and translation across the globe. In other words, if you were to just give set builder notation encrypting this specific set to another person, they can write down an arbitrary number of elements of this set. However, if you were just to give the 5 elements of this set to a person across the globe, then it would have been way more harder to deduce what element comes next. So it's very easier just to give it in set builder notation because it's finite, it's concise, and it's very useful. Now that we've talked about that, let's move on to the order axiom. Now in our previous video, we talked about the 5 most fundamental axioms in mathematics. Now these 5 most fundamental axioms form a field. Now if we add the order axiom into these 5 axioms to become 6 axioms, we're going to form an ordered field. Now the ordered field implies a specific subset of the original field, which is called the positive elements. And this has 2 properties. So we can say P is a subset of F, which is a field. And we're going to be saying that number 1, if we have elements A and B in P, which is the positive elements, A plus B is in P, and A times B is in P. Now if we consider number 2, over here, we have to consider the second property. Now, the second property states that we have A in the field F, and we're going to be saying that if A is in the field F, then A can either be in the positive elements or negative A can either be in the positive elements. Now, the arrow is just representing inside, rather than the traditional inside, or is the element of symbol. So as you can see over here, this first characteristic or property is very self-explanatory, but the second one is a little bit more confusing. So if you think about it, if A is in the positive elements, that means A is positive. But how can negative A be in the positive elements, as many of you might wonder? But the thing is, A can be either positive or it can either be negative. When people just see A, they see there's no negative sign, hence it's positive. But actually, it can also be negative. If it's positive, then A is in P. But if it's negative, then you have to multiply by -1 to make it positive, so negative A is in P. And that's what the second characteristic or property is representing. So that's why it's very useful. Now, if the field satisfies the positive elements properties and the order axiom, which is just as we discussed, then it's considered an ordered field. It's important to realize that the positive elements are non-empty. Okay, now let's talk about the absolute value of x before we move on to our proof. The absolute value of x can be written as a piecewise function. It can be written as x when x is greater than or equal to 0, and negative x when x is less than 0. The primary reason in which we write this is because if we were to, once again, transfer this piece of knowledge to another person on the globe, they can understand it. Like set builder notation, this is a very concise and finite way in order to transfer mathematical knowledge from place to place. Now, that's why it's useful, but also it can decode and encrypt some of the most fundamental important concepts in mathematics, like the absolute value. We talked about set builder notation over here. Like that, we have the absolute value piecewise function. Now, although it's called piecewise function, we can just define this to be a type of notation in one sense. So the absolute value of x is equal to x if x is greater than or equal to 0, or negative x when x is less than 0. If we have 5, that's greater than or equal to 0. So the absolute value of 5 is just 5. If we have negative 5, since x is less than 0, we have to multiply by -1. So -1 times -5 is just going to become 5. Okay, now that we've talked about that, let's move on to our proof. So our proof over here is more complicated than the proof that the square root of 2 is irrational. Now we're stating that the absolute value of A is less than or equal to B if and only if negative B is less than or equal to A, which is less than or equal to B. Now we have if and only if, which means that this is true both ways. And this makes it significantly harder. So we have to prove this both ways. So let's first prove it in the more easy way. And we have to write it in the formality of a proof. So let's assume that the absolute value of A is less than or equal to B. So for one, we're going to prove this part, assuming this part. Then after this, we're going to prove this part, assuming this part, because it's if and only if, which means that since we have if and only if, this is true both ways. Or it might not be, so we have to prove it. So, true this way, true that way, so we have to prove it. So we have to assume both ways. So this is a condition on that, that's a condition on this. Okay, so we're assuming that the absolute value of A is less than or equal to B. Now we're going to be noting a specific proposition. Note that the negative absolute value of A is less than or equal to A, which is less than or equal to positive absolute value of A. Now, substituting absolute value of A is less than or equal to B, we get negative absolute value of A is less than or equal to A, which is less than or equal to positive absolute value of A, which is less than or equal to B. Now, as you can see, A must be less than or equal to B, because A can be less than or equal to absolute value of A, which is less than or equal to B. So therefore, A is less than or equal to absolute value of A, which is less than or equal to B. So A is less than or equal to B, and this proves this part of the thing we're trying to prove, but we have to prove this part as well. So now, we're going to be doing an algebraic manipulation. So we're going to be saying that the absolute value of A is less than or equal to B, and now we're manipulating it so that negative absolute value of A is greater than or equal to negative B. Substituting once again, we get negative B is less than or equal to negative absolute value of A, which is less than or equal to A, which is less than or equal to positive absolute value of A, which is less than or equal to B. And in doing so, we see that A, or negative B, is less than or equal to A, which is less than or equal to B, and proves this. So we've proved it in one direction, and we can write the proof symbol, but we have to prove it in the other direction as well. So let's prove it in the other direction. Now we're going to assume that negative B is less than or equal to A, which is less than or equal to B. So, case number one. If A is greater or equal to 0, then absolute value of A must be equal to A. So therefore, if A is less than or equal to B, absolute value of A must be less than or equal to B. So we've proved this in a little bit of the positive sense. Now, let's prove it in the negative sense. So A is less than 0. Now, if A is less than 0, then A is equal to negative absolute value of A. Considering that negative A equals positive absolute value of A. Okay, now that we've got this, instead of considering this part, we consider the other part. We consider negative B is less than or equal to A. Now plugging in that A is equal to negative absolute value of A, we get that negative B is less than or equal to negative absolute value of A. Multiplying by negative 1, we see that B is greater than or equal to, because we have to switch the sign, greater than or equal to absolute value of A, which proves that absolute value of A is greater, or is less than or equal to B in the negative sense, which we have proved in the positive sense and the negative sense. Therefore, we're proving this statement in this way. So we've proved it both in that direction, and we've proved it in this direction. So we've proved this when this is a condition on this, and we've proved this when this is a condition on this, and we've proved this when this is a condition on this. Now that we've talked about that, we can make this video to an end. If you like this video, if you like this channel, please subscribe to learn more. Thank you.